Hello everyone, my name is Frans Marcelino Purba. Now I will presenting my presentation. This topic is heat treatment of steel. Supporting lecture, Professor Dr. Tjokorda Gde Tirta Nindhia, STMT, M.Eng History Engineering, Metalurgi Mechanical Engineering Study Program, Faculty of Engineering, Udayana University. Reference is Metalurgi for the non-metallurgy second edition, edited by Arthur Sheridan. Next is the topic. The first topic is the iron carbon system. Next is common pieces in steel. Next is critical temperatures and transformation diagrams for each annealing and normalizing. And next is types of annealing treatments. Next is furnace heating and induction heating, hardening and tempering, cold treating of steel. Next is gas hardening, and finally is the heat treating equipment. The iron carbon system. Carbon plays an important role in treatment because it expands the temperature range of oxide stability. Higher carbon content lower the temperature needed to maintain steel such that iron atoms rearrange themselves to form an FCC lattice structure. Under normal conditions, astemcy cannot exist at room temperature in plain carbon steel, but only at elevated temperature with the question area or G bounded by the lines A, G, F, E, G in this picture. Iron carbon system is pieces diagrams and graphical representation of the pieces or different arrangements of atoms that a substance can exist in under various conditions of temperatures and pressure. For iron carbon alloys, the pieces of primary interest are the first is iron. This piece stable at low temperature and low carbon concentration. It has a body-centered cubic BCC crystal structure. Steel is austenate. Austenate from thinner temperatures and or high carbon concentration. It has a centered cubic of FCC crystal structure. Then 3 is cemented. Cemented is a compound of iron and carbon with the chemical formula Fe3C. It is relative hard and brittle and exists at high carbon concentrations. And next is common pieces in steel. The first is cemented and fluid formation. Cemented and fluid formation are intimately related processes that occur during the cooling of constant types of steel. Here's how they form. The first is cemented formation. Cemented form when the carbon concentration in austenate exceeds the solubility limit of carbon in iron at a given temperature. This typically happens at high temperatures. The exact maximum cemented formation depends on factors such as temperature, carbon concentration, and cooling rate. 2 is pellet formation. Pellet is a polymer mixture structure consists of alternate layers of ferrite and cementite. It's formed when austenate transformed into a mixture of ferrite and cemented upon cooling. The neotic reaction in the iron carbon system occurs at a specific temperature known as the exotic temperature about for pure iron carbon alloys. Next is ferrite tends to grow along the austen grains boundaries. When the extract temperature is reached, the remaining austen transform into mixture of ferrite and cemented with the distinctive lamellar bands of ferrite dispersed between the boundaries of the scaled protected ferrite. Gravitation and the formation of spherical beads are accompanying mechanisms of periodic composition. The rate of decomposition is temperature dependent for both mechanisms, and the mechanisms have different active dynamics. As shown in that picture, gravitation is the usual mode of periodic decomposition at temperature below approximately, and the formation of spherical carbohydrates can be expected to predominate at higher temperatures. Different appearance of ferrite and cemented consist of ferrite when examined by optical or light microscope and scanning electron microscope or HAM. Polish specimen in chemical extract such that plated start out in relief. Picture A is an optical microscope at Low magnification, the main splatters appear as dark lines, and B is when fitted high magnification with SAM, the carbide base appears white. Alloying affects hardenability in addition to carbon alloying elements also affect to hardenability and the tempering response of steel in types or hardenability. Alloying elements can be spared according to whether they are a stain stabilizer or ferrite stabilizer. Ferrite stabilizer get a much lowering precision than the stain stabilizer for an equivalent increase in hardenability. 2 is martensite. The microstructure of plate martens have circling regions of resistance acting which appears as the region surrounding the plate and picture at 940 because the plate marten structure is not 100% of the microstructure. It appears more distant in micrographs lead martens and this picture at 950. Okay, this picture is the grace and the hardness of metals with separating temperature for various carbon contents. So the decrease is hardness with separating temperature for a number of carbon levels. Plain carbon of low elementality still can be tempered in lower and higher temperature range, depending on the blend's properties required. The next is benefit. Benefit from when Austin transformed during curling into a mixture of ferrite and cementite, similar to ferrite formation. The microstructure of magnetic particle consists of fine ferrite, needles or plates embedded in a matrix of carbon and rich elstrin. The magnetic transformation occurs below a well-defined beneath start temperature, and the friction transformation increases with decreasing temperature. With this method, it is possible to map out when structures can form. Output is the temperature composition coordinates on the base diagram below at the A1 temperature as summarized in this picture. Next is critical temperatures and transformation diagrams. The critical temperatures of steel define either the onset or completion of a phase transformation. The important critical temperatures is steel treatment is the first is A1 critical temperature for the start of the transformation to a state, and the scaled treated temperature which is aluminum temperature required for a state to form A1 is also referred to as the lower critical temperature. And 2 is A3, critical temperature for complete transformation of the A plus 2 phase mixture into 100% acetylene referred to as the upper critical temperature. A3 is the high temperature boundary of the A plus solid solution phase region with carbon content below the acidic composition of 0.77%. And 3 EACM, critical temperature for complete transformation of the G plus Fe3 phase mixture into 100% acetylene. The X critical temperature is the high temperature boundary of the cementite in solid solution with acetylene in hypertectoid steels. C is 0.77% Celsius. However, continuous cooling diagrams are very critical tools in hot treatment. Continuous cooling diagrams for the phase formation as a function of cooling rate. This type of diagram is very useful because cooling rates are a key process factor in quenching or cooling operation. This ancient the critical use of CCT diagrams as a tool based on party thickness and cooling medium. Computer simulation are also becoming more effective in modeling phase transformation. Next is annealing and normalizing. General annealing thermal cycles. Annealing cycles are varied according to the temperature and the method of cooling used. Annealing temperatures may be classified as the first is subcritical annealing or below the lower critical temperature A1. 2 is intercritical annealing or above A1 but below the upper critical temperature. A3 in hypertectoid steels or ACM in hypertactile steels. And 3 is supercritical annealing to achieve full extinction of antibody hyper or hypereutactile steels. Full annealing. The temperature for full annealing are typical 50 above the upper critical temperature A3 for hypotactic steel and the lower critical temperature A1 for hypotactic steel. And like this picture, okay, the iron carbon binary phase diagram showing region or temperature for full annealing and various other head treatments applied to steels. It is referred to as full annealing because it achieves full obtention of hypotactile steel. Next is types of annealing treatments. Stress relief annealing. Annealing if surface temperature below X1 includes the different temperature region, like this picture. Okay, carbon. Next is recalculation annealing. When cold worked metal are heated to sufficiently high temperature, the badly deformed cold worked grains are replaced by strain-free grains. This process is referred to as recrystallization, which is distinct from the recovery process during stress relief. Next is spheroidizing. Depending on the time temperature exposure of a steel, the cemented carbohydrates in a steel can form different morphologies, such as the lamellar cemented perlite or a network of cemented along pure alternate grain borders in a hypertactile steel. Now, normalizing of steel. Steel of normalizing is a thin grain size, make its structure more uniform, make it more responsive to hardening into improved mechanibility. This picture compares the time temperature cycle of normalizing to that of full annealing. Comparison of time temperature cycles for normalizing and full annealing, the slower glowing of annealing result in temperature transformation to ferrite and ferrite and closer microstructure than does normalizing. Next is furnace heating and induction heating. Like the picture about furnace and figure and 9 to 526 are a basic type of bed furnace. More complex configuration allow for horizontal loading and like the picture and our vertical loading of the workpiece into the furnace. Furnace heating and induction heating are two common methods used for heating materials, particularly metals, in various industrial processes. Let's look at method. The first is furnace heating. Furnace heating involves placing the material inside a furnace or oven by heating into the desired temperature. Furnace can be powered by different energy sources such as electricity, or gas, or oil, depending on the specific requirement of the heating process. And two is induction heating. Induction heating utilizes electromagnetic induction to heat electric conductive materials. A high frequency alternating current or AC is present in induction coil, generating a rapidly changing magnetic field. When the electrical conductive material is placed with the coil, eddy currents and induced in the material, leading to resistive heating due to Joule heating. In summary, both furnace heating and induction heating are effective methods for heating materials. Each offering unique advantage depending on the specific requirements of the heating process, effect of heating rate, or transformation temperature. When full annealing or full obstination is required on important factor. Is the effect of heating rate on the upper critical temperature AC3 for complete obstination. Next is hardening and tempering. Hardening, also known as quench hardening, is simply quenching. Involves heating the metal to a critical temperature above its obstination temperature and rapidly cooling it, typically by immersing it in a quenching medium such as water, oil, or air. Next is tempering. It's a process that follows hardening and involves returning the hardened metal to temperature below its lower critical temperature and cooling it at a controlled rate. Compression of cooling rates and temperature gradients workpiece pass into and track the maintenance transformation rank for a conventional quenching and tempering process and for intermediate quenching process. The next picture A is conventional quenching and tempering process that use oil, water, or polymer quenching. And B is more quenching, which uses either a salt or hot oil as quenchant. C is tempering, which uses salt as a quenchant. And D is isothermal quenching, which uses either salt or hot oil as a quenchant. Gas hardening. Gas hardening is a generic term used for several processes that put a hard-wear-resistant surface layer on a part. The fusion methods include the first is carbonizing, two is nitriding, carbonizing, nitrobrewerizing, and brooding, tritonium carbon diffusion, and next is Toyota diffusion process. Localized handling methods for gas hardening include the first is flame hardening, next is induction hardening, laser hardening, electron beam hardening, ion implantation, and finally is use of air lamps. This method of localized heating are well suited to selective surface hardening. However, selective carbonizing and nitriding are suitable. Next is heat treating equipment. Most furnaces are loaded with a charge that allows for a pre-established heating cycle. After the cycle is complete, part might be cooled in the furnace after the heat is turned off, or a method such as quenching in water or oil may be used. Types of bed furnace include the first is box furnace, two is car bottom furnace, next is pit furnace, bell and hot furnace, elevating hot furnace, and integral furnace or IQ furnace, and finally is tape or furnace. Continuous furnace like this picture are bicycle of the in one and out the other. Type on are ordinarily used for continuous polymer production. They can accommodate a variety of heat treatment. Examples are the one is roller hot furnace, two moving hot furnace, three pusher furnace, and four is shaker hot furnace, and five is rotary return furnace. Heat treating equipment compress a wide range of tools and mechanically used in the heat treatment process of metals. They include furnaces, oven, induction heaters, quench tanks, and various ancillary equipment. Uh, Thank you. Hopefully it is useful and can be understood clearly. And I say thank you and see you in the next topic. Thank you.